Three-phase circuits. In this video, we'll discuss the analysis of three-phase AC circuits. Before analyzing a three-phase circuit, why you are going for a three-phase system? That we'll see. That is the advantages of three-phase system. Here, some of the advantages are listed here. The most of the electric power is generated and distributed in three phase. Whatever you are generating and the transmitting electricity, it is in a three phase. That is why you are going for the three phase system. We'll see why the advantage of a three phase system. The instantaneous power in a three phase system can be constant. That is, we know that the instantaneous value of a single phase supply, okay, that is the pulsating in the nature. However, in the case of a three-phase system, we are getting a constant power. That is why you are going for the three-phase system. The third advantage is the amount of power. The three-phase system is more economical than the single phase. That is, one is the advantage of the three-phase system is you can transmit the electricity with a high voltage and it is most economical. If you are having a single phase, then you have got a two wires. If you want a three such types, and we need a six wires. If you are going for a three phase system with a proper connection of either star and delta, then the wire reduces to either 3 or a 4. However, we are getting a three phase system over and above a single phase system. That is, it is most economical. In fact, the amount of wire required, the same thing I am telling here. In fact, the amount of wire required for a three-phase system is less than that required for any equivalent single-phase system. If you have got the transmitting a power of 10 kVA with a single phase, that is require the three such system having a 6 wires, the cost is increasing. The same 10 kVA can be transmitted with only the 3 wires or 4 wires. With a star 3-phase connection, there are two range of voltages. Two range of voltages we are getting in the case of a 3-phase system. Higher voltage and the lower voltage if it is star connected. That is another advantage of connecting, advantage of a 3-phase system. Then a 3-phase machines can be smaller than a single phase one for the same power output. For example, if you are designing 2 kVA single phase motor, the size of the machine is the more. However, if you are designing a 3-phase machine, then the size of the machine for the same capacity is lesser, thereby the cost of the machine is also the reducing. These are the advantages of a 3-phase system. That is why we are going for a 3-phase system. Next, what do you mean by a 3-phase system? Then how to generate a 3-phase voltage and the current? We know that to generate the electricity, we need three things. For generating electricity, we need three things. One is we need the field. Second one is the conductor. A third one is the relative motion between field and conductor. We know that according to Faraday's laws of electromagnetic induction, when the conductor cuts the magnetic field, there is a induced voltage in the conductor. Or the flux linking with the conductor is changing, then there is an induced. There are two types of induced voltage. One is called as statically induced voltage, wherein the conductors are stationary, the field is rotating. If the field linking with the conductor changes, there is an induced voltage, that is statically induced voltage. The same principle is used in the three-phase alternator. That is, the machine which generates the electricity in the AC is called as AC machine, that is called as three-phase AC generator. Also, it is called as the same as alternator, or it is also called as the synchronous generator. It's one and same. That is, you are generating three-phase electricity with a three-phase AC generator, or it is also called as three-phase alternator or a three-phase synchronous generator. We know that in the case of the alternator, the conductors are stationary and field is rotating. Consider here a generator. If you have got only one coil, if you have got only one coil, then if there is the field, the two-pole machine with N and S, if it is rotating with omega radians per second, then the voltage induced in this one is called as single phase alternator. In a three-phase alternator, we have got a three windings, three identical windings. They are displaced 120 degree, and there is a rotating magnetic field. For example, here we have got a stator of a alternator. We have got three windings, that is, I'll call this is a winding 1, or it is called as coil A, and the second coil as, call this as A, okay, and the second one is this is A, B, this I'll call as C. This is a winding C. Okay. Here, in the case of a three-phase alternator, we have got a three identical coils. Three identical coils means they are made up of same material. The number of the turns in the coil is the same. All the three coils are the identical, but the phase displacement between A and B is 120, B to C is 120, C to A is 120. Then I have got the field system. I have got N and S. It is excited by a DC source. Then it is rotating in anti-clockwise direction with omega radians per second. Then here there are three voltages. One is the voltage induced in the coil A, voltage induced in the coil B, and voltage induced in the C. The magnitude of induced voltage in coil A, B, and C is same, but there is a phase displacement between voltage induced in the A and B by an angle of 120. Between B and C is another 120, or in other words, between C and A it is also 120 degree. Then how it is looks like, that we'll see. That is, we have got take a reference. I have got, I'll make the division of 30 each, so that I can draw 30, 60, 90, 120, 150, 180, 210, 240, 270, it is 300, 330, and so on. We'll start with drawing the waveform of first. I will draw the phase A, or the coil A, that is taken as a reference. Therefore it is reaching its maximum value here, 90. Then 180, it is reaching its zero value. Then 30, 40, 30, 60, and 90. It is here and it is reaching here. Okay, we'll draw a sinusoidal waveform having R phase, here. This is the waveform for R phase. Then what is the phase displacement between the induced voltage between A and B? It is 120 degree. Then that is, the phase B is lagging phase A by an angle of 20. Therefore its zero value start from 120. That is, it will start from 120 here. That is 30, 60, 90, means it is attaining its maximum value here. 30, 60, 90, it reaching its zero value here. Then it is okay. That is, it will start here. Then it has got a zero value here. Then it is. Now the third phase, that is phase C, which lags B by an angle of 120, or it lags A by an angle of 240, means it has to start from 240. That is here. It will start here. See here, Here it is 120. Then here it is the 240. It will start at 0 value from 240. Therefore, here 30, 60, 90. It has got maximum value here. Therefore, it will goes like this. Means if you are drawing these waveforms 30, 60 and 90, its maximum value here. That is, if you are drawing a backward, the waveform, that is what we are getting here is getting here. This R phase. Means starting point is 120. Just I am reproducing in the backward direction. Similarly, you can start this. This is 30, 60 and 90. It has got here value. That is here. And 30, 60, 90. It reaching 0 value here. And if we are putting 30, it is 60. Then this is a value. This is how we have to draw the waveform for R, Y and B or A, B, C. This is the waveform for A coil, waveform for B coil, and is a waveform for coil number C. You can see here clearly the second coil starts its generating the voltage 120 lagging the A. Its 0 value is lagging by 120. Then with respect to A, and if you are comparing the C, it is lagging an angle of 240 with respect to A or 120 with respect to B. Therefore, you can write the equations for these values using A coil voltage as a reference. That is, I call EA is equal to E max sine omega t, because this I am taking as a reference. That means it is started with 0. Then what about EB? EB is lagging A by an angle of 120, but all the three coils are similar. The magnitude, the maximum value is remains the same for R, A, B, C coil. Therefore, I'll write this as EB is equal to E max sine omega t minus 120. Right? This is a E max sine omega t minus 120. Then how we are writing the equation for C? It is EC is equal to E max sine omega t minus 240. If you are drawing a vector diagram with their RMS values, then you take EA as a reference. That is, I'll draw this with a RMS value. That is your EA. Then EB is lagging EA by an angle of 120. Therefore, you have to draw a vector EB lagging EA by an angle of 120. 120 degree. This is your EB, where EA, EB are RMS value, where EA, EB, EC, small EA, EB, EC are the instantaneous values. Then Y, it is lagging EA by an angle of 240, having the same magnitude. To draw the same magnitude as EA, EB. That is, it is your EC. Then it is lagging EA by an angle of 240 degree. Therefore, you are writing EA, EB and EC. That is, the summary of the generation is here in the three-phase alternator we have got three coils, three similar coils. These are displaced by 120 degree and a field system is rotating with the angular velocity omega. Therefore, because of the coils are identical, the induced voltage in all the three coils A, B, C are equal in its magnitude. However, they are lagging 120 degree each other. That is, the induced voltage in B lags A by 120 and in the coil C it lags B by 120 or it lags A by 240. That is quite evident from this vector diagram. That is A, B and C the waveforms. Here are the EA, EB and EC are the voltages. Okay. Now we'll define some of the aspects of a three-phase circuit. These are very important while analyzing the circuit. Okay, the first one is the phase sequence. The first one is the phase sequence. Phase sequence. The phase sequence is nothing but the order in which the voltages in the three phases of an alternator reaches maximum positive value, values is called phase sequence. That is, in this case, if you are observing here coil A is reaching its maximum value first time, then coil B is reaching its maximum value in the second sequentially, and in the third case it is C is reaching its maximum value third. Therefore, the sequence of the phase is A, B, C. That is why the phase sequence is, in this case, is phase sequences A, B and C. If C is reaching maximum value second time, then the phase sequence is ACB. Like that. It is depending upon how they are reaching the maximum value. This is for the today's discussion. Then how there is a generation of a three-phase circuit. Here there are three coils and it is rotating. There is a field is rotating. Because of that, there is a induced voltage in the three similar coils. The induced voltage magnitude remains constant. However, there is a phase displacement of 120 degree with each other. In the next video, we will discuss what are the different types of the connection in the three-phase circuit. Then what is the relation between the voltage, current, and there is how we are calculating the active power, reactive power and the apparent power in a three-phase circuit.